Welcome. Today we're diving into the fascinating world of computer architecture, focusing on the von Neumann model. This architecture forms the backbone of most computers we use today. Named after the brilliant mathematician John von Neumann, this design revolutionized how computers process data and instructions. In this video, we'll explore its core components, how they interact, and why this architecture remains so influential. Whether you're a tech enthusiast or just curious about how computers work, you'll find this journey insightful and engaging. Let's start by understanding what makes the von Neumann architecture so special. John von Neumann was a Hungarian-American mathematician, physicist, and computer scientist. His contributions span many fields, but his work in computing changed the world. In the 1940s, he proposed a new way to design computers, making them more flexible and powerful. His architecture allowed computers to store both data and instructions in the same memory, a concept that was groundbreaking at the time. This innovation paved the way for modern computing, influencing everything from personal laptops to supercomputers. Understanding his vision helps us appreciate the technology we use every day. Before the von Neumann architecture, computers were limited and inflexible. Early machines had separate storage for instructions and data, making them difficult to reprogram. Von Neumann's idea was to use a single memory for both, which made computers much more adaptable. This shift meant that computers could be programmed to perform a wide variety of tasks simply by changing the instructions in memory. This was a major leap forward, setting the stage for the rapid development of computing technology in the decades that followed. The von Neumann architecture is built around a few key components: the central processing unit, CPU, memory, input-output devices, and a system bus. Each part plays a crucial role in the operation of a computer. The CPU acts as the brain, executing instructions and processing data. Memory stores both the instructions and the data the CPU needs. Input and output devices allow the computer to interact with the outside world, while the system bus connects everything together. Let's take a closer look at each of these components. At the heart of the von Neumann architecture is the CPU. It's responsible for fetching instructions from memory, decoding them, and executing them. The CPU itself is made up of two main parts: the arithmetic logic unit ALU, which performs calculations and logical operations, and the control unit, which directs the flow of data and instructions. Together, these components enable the computer to perform complex tasks quickly and efficiently. The CPU's design is a key reason why computers are so powerful today. Memory in the von Neumann architecture serves as the central storage for both data and instructions. This unified approach means that the CPU can access everything it needs from one place, making processing faster and more efficient. Memory is organized into addressable units, allowing the CPU to quickly locate and retrieve information. This design simplifies programming and enables computers to handle a wide variety of tasks. Without this innovation, modern software would be much more difficult to create and run. Input and output devices are essential for communication between the computer and the outside world. Input devices like keyboards and mice allow users to send data and commands to the computer. Output devices such as monitors and printers display results and information. In the von Neumann architecture, these devices are connected to the CPU and memory via the system bus, ensuring smooth data transfer. This setup makes computers versatile and user-friendly, supporting a wide range of applications. The system bus acts as the communication highway within the von Neumann architecture. It connects the CPU, memory, and input-output devices, allowing them to exchange data and instructions efficiently. The bus consists of multiple lines for data, addresses, and control signals. This structure ensures that all components can work together seamlessly, making the computer operate as a unified system. The system bus is a critical part of what makes the von Neumann architecture so effective. In the von Neumann architecture, instructions are processed in a cycle known as the fetch-decode-execute cycle. First, the CPU fetches an instruction from memory. Next, it decodes the instruction to determine what action is needed. Finally, it executes the instruction, performing calculations or moving data as required. This cycle repeats continuously, allowing the computer to carry out complex programs step by step. Understanding this process is key to grasping how computers operate at their core. One of the defining features of the von Neumann architecture is its unified memory. Both program instructions and data are stored in the same memory space. This means the CPU can access and modify instructions just like data, making computers highly flexible. However, this also introduces the possibility of errors if instructions are accidentally overwritten. Despite this risk, the unified memory model greatly simplifies computer design and programming, which is why it's still widely used today. The von Neumann architecture offers several key advantages. Its simplicity makes it easy to design and build computers. The unified memory allows for flexible programming, enabling computers to run a wide variety of applications. Additionally, the fetch decode execute cycle streamlines processing, making computers efficient and reliable. These benefits have helped the von Neumann model remain the standard for decades, powering everything from early mainframes to modern laptops. Despite its strengths, the von Neumann architecture has some limitations. The most notable is the so-called von Neumann bottleneck. Because instructions and data share the same bus, only one can be accessed at a time, which can slow down processing. This bottleneck becomes more pronounced as computers get faster and more complex. Understanding these limitations is important for appreciating how computer architecture continues to evolve. To address the bottleneck, another architecture called the Harvard model was developed. Unlike von Neumann, Harvard architecture uses separate memory and buses for instructions and data. This allows simultaneous access, improving performance. However, the von Neumann model remains more common due to its simplicity and cost-effectiveness. Comparing these two architectures helps us understand the trade-offs involved in computer design. Today, the von Neumann architecture is still the foundation for most general-purpose computers. From desktops and laptops to servers and embedded systems, its influence is everywhere. Even as new designs emerge, the basic principles of the von Neumann model continue to guide computer engineering. Its flexibility and simplicity make it ideal for a wide range of applications, ensuring its relevance in the digital age. You might not realize it, but you interact with von Neumann architecture every day. Your smartphone, laptop, and even smart appliances use this model. Its design allows these devices to run complex software, connect to the internet, and perform countless tasks. The next time you use a gadget, remember that von Neumann's ideas are working behind the scenes, making modern life possible. The flexibility of the von Neumann architecture also introduces security challenges. Because instructions and data share the same memory, malicious software can potentially alter instructions, leading to vulnerabilities. This is why modern computers use various security measures, such as memory protection and access controls, to safeguard against attacks. Understanding these risks is crucial for building safer, more reliable systems. John von Neumann's vision has left a lasting legacy in the world of computing. His architecture not only shaped the development of early computers, but also set the standard for future generations. The principles he established continue to influence hardware and software design, ensuring that his impact will be felt for years to come. Von Neumann's work reminds us of the power of innovative thinking and its ability to change the world. As technology advances, new computer architectures are being developed to overcome the limitations of the von Neumann model. Quantum computing, neuromorphic chips, and other innovations promise to revolutionize the field. However, the foundational ideas of von Neumann continue to inform and inspire these new designs. The future of computing will likely blend old and new, building on the strengths of past architectures while exploring new possibilities. Let's quickly recap some key terms: CPU, memory, input-output devices, system bus, fetch decode execute cycle, and unified memory. Understanding these concepts is essential for grasping how the von Neumann architecture works. Each term represents a building block of modern computers, and together they form the foundation of digital technology. In summary, the von Neumann architecture revolutionized computing by introducing a simple, flexible, and powerful design. Its core components, CPU, memory, input-output devices, and system bus, work together to process instructions and data efficiently. While it has some limitations, its influence on modern technology is undeniable. Understanding this architecture helps us appreciate the incredible machines we use every day. As we look to the future, the von Neumann architecture remains a cornerstone of computer science education and engineering. Its principles continue to inspire new generations of innovators and researchers. By understanding its strengths and limitations, we can better appreciate the ongoing evolution of technology and anticipate the exciting developments yet to come.